Welcome in, everyone. In this video, I'm going to go over the first derivative test. And in order to do that, the first thing I will cover is the increasing and decreasing intervals of a function. Then we'll talk about the actual first derivative test and how it can be used. And then I'll get into some examples that use the first derivative test. Let's get into it. In order to get the idea of the first derivative test across as quickly as I can, I want to first just look at the intervals where a function is either increasing or decreasing. So here we have a function, it's quadratic, and this is the graph of it. Before calculus, you needed the graph of the function. As you move left to right, you can tell that the function is increasing up until a certain point, and then it starts decreasing. And you were just able to list that off. It was moving up left to right from, let's see, negative infinity to 4, and it was decreasing from 4 to infinity. But in calculus, you are unable to use the graph. We've got to do things algebraically. So what the heck are you supposed to do to figure out where a function is increasing or decreasing? Well, being calculus, we're going to use the derivative to help describe the original function. So let's take a look at the derivative of this function. I want to use f prime of x will equal, by the chain rule here, it'll be negative 3 times 2x minus 4. And the derivative of the inside function here is 1. The derivative of negative 2 is just 0. So we have this equation to simplify. So the derivative really simplifies down to negative 6x plus 24. All right. This lesson in calculus, leading up to this lesson in calculus, you've learned about critical values. They're probably important here. So let's find a critical value for this function. You can find the critical values by setting the derivative equal to 0, and when you do that, you'll get x equals 4. Now I want to stop right here. This is a critical value. And I just want to point out that at the graph, when x equals 4, that's the exact value that this graph stopped increasing and started decreasing. But how are we supposed to figure that out? Well, in order to figure it out, we can just use a number line. And I'm going to make a very small sign chart here. X equals 4. I'm going to notate where that critical value is, give myself a boundary. So at that critical value to the left of it, something is happening. Either the function is increasing or decreasing, and to the right of it, either the function is increasing or decreasing. But how are we supposed to figure that out? Well, we're going to take some test values. So I want to pick a number less than 4. Maybe I pick 0. Generally speaking, if you can pick 0, pick 0. And then to the right, maybe I pick 5. And still, picking these values 0 and 5, that doesn't make much sense on how I'm supposed to make sure this is increasing or decreasing. And the magic there lies within the tangent lines. We are talking about derivatives after all. So when you look at a tangent line of any point, say this one, to the left of x equals 4, so any point to the left of x equals 4, like this one, or this one, you can imagine the tangent line there. All tangent lines to the left of x equals 4 have positive slopes. So we can make this jump in thinking that if any tangent line has a positive slope, then the graph is increasing, or the function is increasing in that interval. And a similar idea works to the right of x equals 4. We can take this point right here. There's a tangent line, negative slope. there's a tangent line, negative slope. There's a tangent line, negative slope, negative slope. So if we evaluate a number to the right of x equals 4 and find the slope of a tangent line, we'll be able to tell if that interval is decreasing. If it's negative, right? If we get a negative tangent line slope, then it's decreasing. So we're going to take advantage of that. So why don't we substitute 0 in for x in the original derivative? That will be 24. But again, I don't care about the number. I care about whether that number is positive or negative. So it's greater than 0. That means increasing to the left of 4, which is exactly what we can see in the graph and in our answer. If we substitute negative 5 in for x in the derivative, you can see that we would end up getting something like negative 6. And that is less than 0, which means the graph or the function would be decreasing to the right of 4, which again matches up with what we had on the graph and our answer. So we are using the derivative to find characteristics about the original function. How does this play into the first derivative test, though? The first derivative test. Suppose c is a critical value of a continuous function f, and that f is differentiable on a small interval containing c, except possibly at c itself. Then moving from left to right, if the derivative values change from negative to positive at c, then there's a local minimum for the function f. And something similar happens when the derivative values change from positive to negative at c. There's a local maximum for the function f. And then if the derivative values don't change, then there's no maximum or minimum. I want to take a moment to point out that these local max and local min that we end up finding over here, we are using the derivatives to find more characteristics about the original function. So when we say we've located a local min or a local max, that exists on the original function. And this is helpful in context with what you saw on the last slide, because if we have a function and we can find out where the intervals are increasing or decreasing, or in other words, find out where the derivative changes from negative to positive, negatively sloped lines to positively sloped lines, then we can find a min or a max. So take, for example, f graphed at the bottom of this slide on the left. If we have negatively sloped tangent lines, eventually, with the graph that we have, it levels out to a zero-sloped tangent line. And a zero-sloped tangent line, or horizontal tangent line, is where the max or min will be on the original function. And then all of these slopes become positive afterward. So the derivative changing from negative to positive will give you a min. Decreasing to increasing, negative to positive. Similarly, we can do something with the maximum here. These all have positively sloped tangent lines. Eventually, for this graph, we hit a zero slope tangent line, which is, again, a critical value because this x value would make the derivative equal to 0, aka horizontal line. And we can see that afterward there are negatively sloped tangent lines. And so when you go from increasing to decreasing, or positively sloped tangent lines to negatively sloped tangent lines, we get a local max. And then if the derivative doesn't change, you get neither a max nor a min. But the fun part about the first derivative test is that we have to do this without a graph. We're doing it all algebraically. And how that looks is we're going to have to find the critical values. So we can take the derivative of this, f prime of x, equaling 2 minus 2x. And we're finding the critical values because that's where a function has extrema, either a maximum or a minimum. So here we have this, we have to check for denominators. Remember, critical values are where the derivative equals 0 or where the derivative is undefined. But since we're dealing with a polynomial, there are no undefined values here. So we just have to set this derivative 2 minus 2x equals 0 and solve for x to find the only critical value of 1. So that's the first part 1, find all the critical values. You can see it here. The second thing that you have to do is find the intervals where the function is either increasing or decreasing. This is how I notate that, very shorthand. And we can do that by setting up a number line and placing our critical value on that number line. And since we just have one critical value, we just have to put one number on the number line. And I'm going to draw a little dashed line like this to hopefully remember that I need to pick two test values because there's one interval to the left of this critical value and one interval to the right of this critical value. So you just have to make sure you're picking critical or test values in the correct interval. And if you can, you want to pick 0. So I'm going to go ahead and evaluate the derivative at these test values. Remember, the derivative at a specific number tells us the slope of the tangent line. So if we substitute 0 in here, 2 minus 0 is 2, but really we care that it is positive. And since it's positive, the tangent line will be positively sloped on that interval. And we can do the same thing for negative 2 if you substitute, positive 2. If you substitute 2 in for x, 2 minus 4 is negative 2. But again, we're mostly interested in the fact that the derivative is negative, which means tangent lines to the right of x equals 1 have negative slopes. Okay, so you can see we go from increasing and decreasing. So we can write those intervals out here, increasing from negative infinity to 1, and decreasing from 1 to infinity. So that was part 2, mostly in orange and blue, so I'm going to underline that here and here. The last piece of this exercise, or example, is to find any extrema. It is best just to call these local extrema because without the graph, we don't know if it will be a local or an absolute extrema. But what we can do is we can just use this graph we made over here to find the intervals where the function is increasing and decreasing, and notice that at x equals 1, from left to right, it stops increasing and starts decreasing. So this will have a local max at x equals 1. But where is that local max? I mean, how high is it? Well, what we have to do to figure that out is remember, we're using the derivative to describe the original function. So if we're trying to find the local max of the original function, we need to take that x value and substitute it into the original function. So if you substitute 1 in for x here, you'll have a local max of 1 at x equals 1. Example 2, we're just going to truck through and do the same thing. So you notice that we have this function f of t equaling this monstrosity on the interval from 3 included off to infinity. So we have a bit of a restricted domain here, so we're just going to have to keep that in mind as we go through and figure out the derivative for this and the critical values and whatnot. Speaking of that, let's go ahead and start with the critical values. The critical values are found by finding the derivative, which is 2t minus 2 all over 2 times t squared minus 2t minus 3 to the 1/2 power. Now, keen-eyed viewers might notice that we can divide the top and bottom by 2. So in order to make this a little bit simpler, I want to do that. T squared minus 2t minus 3 to the 1/2 power. There's a chain rule here. The square root is the same as a 1/2 power, so you can see there's a 1 here over 2 times the derivative of the square root would be a negative 1/2 power, that's why it's in the bottom, times the derivative of the inside function, which is 2t minus 2. All right, that being said, we can find critical values now. From the numerator, we can set t minus 1 equal to 0, t equals 1. Hooray, that one was easy. And we can also set the denominator equal to 0 to find the critical values that make the derivative undefined. So we have t squared minus 2t minus 3 equals 0. If I write the 1/2 power here, I can just square both sides. 0 squared is 0. So we can start with just the polynomial inside. We can factor that t minus 3 and t plus 1 equals 0. And we get that t equals 3 and negative 1. So we have a lot of critical values here, but really we're only concerned about one of them. You can see from the top we got t equals 1. That's not in this interval. Don't care about it, so we're going to go ahead and toss this one aside. What else do we have? We also have t equals negative 1. Don't care about that one. The only one that we are worried about is t equaling 3, because that's what's in this interval. All right. Now I want to go ahead and set up the number line with that one critical value that we are interested in. T equals 3, but that made the derivative undefined. So I'm just going to notate that so I know that the derivative is undefined here. And the testing gets a little bit strange here as well. So if you'll notice, we go from 3 to infinity. That's the domain or the interval where this function is defined for this example. It doesn't make sense to pick any numbers to the left of 3 because we're not worried about it. We're starting at 3. We only have to pick one test value this time, so I'm just going to pick 4 rather randomly. And I want to find f prime of 4. Now you can use whichever version of f prime you want. You can use the unsimplified or the simplified version. I'm going to go ahead and use the simplified version to show that f prime of 4 equals 3 over root 5. Now I know in the last example I didn't write out what the derivative evaluated at a specific value was. Right? I didn't write this number. But if you find that it helps, I encourage you to do that because you can make the comparison a lot easier. I know that number is bigger than 0. So this is increasing. Starting at 3 and going on forever, this is an increasing function to the right. What does that mean? That means for step 3, let's finish step 2 here. We can say this is increasing from 3 to infinity. Okay. Now we move on to the extrema. Is this critical value a max or a min? Well, it is going to be a min because if we start at t equals 3 and it goes up or increases forever to the right, this would be a minimum value. So we can say there is a local min. I don't know what the y value is yet of something at t equaling 3. But we can figure out what that is if we just find f of 3. And when you do that, it ends up being 0. So there's a local min of 0 at t equals 3. Now there is something that I can state here for certain. Seeing as how we start at 3 and move forever to the right, this graph, or rather this function, since there are no decreasing values, I am 100% positive in saying that this would be an absolute minimum of 0. This is the lowest this is the lowest y value the function will ever have if we're only looking from 3 to infinity. And again, that reason is because this graph does not decrease anywhere. So it's a absolute minimum. But answering with local minimum is good enough. One more example. We have g of x equaling x squared over x squared minus 4 on this interval here. And we restricted this interval very much because, again, we have to have a function that is continuous on an interval in order to use the first derivative test. So let's go through the steps. We have to find the derivative first in order to find the critical values. So g prime of x will equal the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Cleaning up the top, you'll get negative 8x. In the denominator will remain the same. So we can do the same thing we did in the last example. Since we have a fraction, we can set the top equal to 0 to give us a critical value of x equaling 0. And right off the bat, I'm excited by this because that critical value is in the interval we're looking at. Hooray! But we can also set the denominator equal to 0 to find out which critical values make the derivative undefined. So when you do that, we can have x squared minus 4 equaling 0. And again, I'm not writing the square here because I can just take the square root of both sides immediately, and the square root of 0 is 0. You can factor this by difference of squares and solve each factor to get x equals 2 and negative 2. But right away this time, we can tell neither of these work because they're not in the interval we're interested in. Okay, so let's check it out. We have a critical value of 0, and so I'm going to go ahead and make my number line. I'm really only interested between the values of negative 2 and 1, so I'm marking those so I know where to limit my test values. And I'm going to pick a test value of negative 1 to the left of 0, and I'll pick 1/2 to the right of 0. And we're going to evaluate the derivative at these test values so we can find out which way the tangent lines are sloping to make a larger discovery about this function. So when you substitute negative 1 into the derivative, I can tell you the numerator becomes a positive 8. In the denominator, when you square negative 1 becomes 1. 1 minus 4 is negative 3. But when you square 3, you get positive 9. So it becomes 8 over 9. Which is bigger than 0. So this is increasing from negative 2 to 0. And when you substitute 1/2 in for x here and here, in the numerator, you'll get something negative, and in the denominator, you'll get something positive. I have no idea what the answers are going to be this time. I just know that this will be negative. So between 0 and 1, it is decreasing. All right. We have an increasing interval from negative 2 to 0 and a decreasing interval from 0 to 1. From there, we can talk about the local maxes and the local mins. using the first derivative test. So there's a local, let's see, if you go from increasing to decreasing, it would top out, there would be a local max here. I don't know where it is. We'll get there when we get there. A local max of at x equals, what is that? 0, right? That's the only critical value we had, 0. But in order to find that local max, we have to substitute this value into the original function. We're trying to find a local max of the original function. Okay, I think y'all get it by this point. But when you substitute 0 into the original function, you get 0. So local max of 0 at x equals 0. One final thing I want to say in this video is that you can definitely apply the first derivative test and find the intervals on which a function is increasing or decreasing with regards to a trig function. I did not get to an example of that, but you would do it exactly the same way as all of this. I hope this video helps you out. Good luck.